All right. So what we have to do today is finish up the last few slides out of chapter 13 and start on chapter 14. So these are the last few things that we're talking about. Rates and rate equations and things like that. All right, so a follow-up question on some of the stuff we were talking about rates and rate equations is what is a catalyst? Right, and the activation energy using our Arrhenius equation was the energy it takes to get from reactants to our intermediate. Up here, intermediate. Right, that was our activation energy. So a catalyst is anything that is added to a reaction to, more appropriately, increase the rate. Oh, yes. Yeah, take cover. Look out. I mean, you're in the room in the building with no windows, so I think we're probably okay. If the power goes out, then we'll know we have an issue. But, where am I at? Okay. Yeah, today is the severe weather advisory week. So, let's see. Now I lost my train of thought, kids. Oh, okay. So here we have, right, we have hydrogen peroxide, and over time it would decompose to water and oxygen, which is what this graph is showing. Right, so on my reactant side, I have hydrogen peroxide. Then as time goes by, right, it'll eventually make water and oxygen. Is this reaction endothermic or exothermic? Exo. How do we know it's exo? Products are lower than. Right, because it's going to release energy compared to where I was. Right. So if the enthalpy, if that's a negative enthalpy, this has to be exothermic. All right, so we could add a catalyst to this reaction, and we would write it like this. Maybe more in a straight line, where you still have the same hydrogen peroxide, but now you add the manganese dioxide, and it still makes water and oxygen. But now the intermediate, the energy required to get to the intermediate is lowered, which means it's more probable that I can go from reactants to products. So a catalyst lowers the activation energy, which means it's just more probable to make products. So how can we figure out what is going to be the activation energy, and what are some ways we can figure out the reaction mechanism for a given reaction? So this is the last section of this chapter called Reaction Mechanisms. All right, so let's say I have the reaction AB plus C makes A and BC. All right, that's my generic equation. I could imagine two different ways to have this work out. Right, that's one option. I have A, B, they spontaneously break in half, and then B goes on to recombine with C to make BC. So let's say I want to do the same thing we did when we had enthalpy, right? You can add the two equations together, right? When we had enthalpy, you had two half reactions, and you combine them together and stuff canceled out, and you added up the overall enthalpy. And we're going to do the same thing with these guys. So in this case, B appears both as a reactant and a product. All right, so B appears both as a reactant and a product, which means in this case, B is considered an intermediate. Right, because it doesn't stay. I don't have B left in the end. My net reaction would be what I'm looking for. All right, that's my net reaction where the B's cancel out top and bottom. I can add them back together. All right, that is one way this reaction could go forward. All right, that's option A for 1. Another choice could be something like this. What if I did this? Let's say I had that as my reaction. In this case, what is considered the intermediate? Right, ABC is the intermediate because it appears both as a product and again as a reactant. Do I get the same final net reaction that I want? Okay. So is there any way to tell which one of these is more correct based on the information we have so far? No, we don't have enough information so far to figure out which one is more likely to happen. All right, so each one of these steps is considered an elementary step. An elementary step describes a possible reaction that could occur. When added together, make it the net reaction. So elementary steps by themselves is not the whole reaction. It's the parts you need to add together to get back to the net reaction that you want. So in order to figure out which one of these two is more likely, we need to start talking about what makes a reaction likely or not likely. So we get a fun new word. Molecularity. You'll never probably use this term again, but it's a fun word to say. All right, molecularity is defined as the number of molecules that participate in an elementary step. An elementary step we defined on the other page, but again, describes possible reaction have to add up to the net reaction and has its own EA and K. Right, activation energy and its own rate constant.
What do you add to
They add up to the net reaction. Sorry, a little sloppy looking there. I don't know why I left this side blank. That's just some spare space. I want to actually go on to the next slide. Sorry. You can draw yourself a little doodle or something there. Come back in color. Alright, so in order to figure out a mechanism, we're going to go by 5 general rules. The first one is, for the net reaction, you cannot assume a simple relationship between the reaction coefficients and the reaction orders. Right, so this is what I've been telling you all I guess semester so far, right? If I have this reaction, right, if that's my reaction, could you give me the rate equation for this? Okay, there's the rate equation and there's the rate law. You can give me the rate equation, right? Rate equation is just based on the stoichiometric coefficients. The rate law is based on what do I need to go and do? Right, I need to go collect some data. So I cannot make a simple relationship between the coefficient and the reactant orders, which is what we say when we're talking about the rate law, the reaction order, those exponents. So I would have to tell you somehow that it's actually, right, somehow you would have to I would either have to tell you or experimentally you'd figure out it's first order in NO and second order in fluorine, right? However, for every rule there's the exception. If I'm talking about an elementary step, the coefficients, the stoichiometric coefficients, do equal the exponents.
So will we be informed on which ones are elementary steps?
I'd have to tell you it's an elementary step or a net reaction. So if I had an elementary step for this reaction over here, that was something like there's just one of the elementary steps, right? We'd have to go through a bunch more in order to get to what we actually want. But for example, for an elementary step, which I would tell you, it's an elementary step, the stoichiometric coefficients are now the exponents. So if we did another one, where, let's say we have an elementary step that looks like this. All right, let's say I have an elementary step that has something that looks like that. Knowing it's an elementary step, what is the exponent that goes with the hydrogen? Okay. Then what is the exponent that goes with the ICL? Okay. Okay. So why is that useful? Besides the fact that I said so. We can use that plus this next rule to figure out mechanisms. So the rate of a net reaction is essentially the same The rate of next reaction is essentially the rate of the slowest step, which if you've ever taken any biology, right, rate determining step should be a familiar phrase, right? We talk about rate determining steps. So let's say I have these two elementary steps. That should be a 2. I wrote over my 2. So 2 NO2s reacting together to make NO, NO3. Alright, so I got NO2 and NO2 coming together to make one NO and one NO3. In my second elementary step, I have NO3 and carbon monoxide making nitrogen dioxide and carbon dioxide. Let's take a look at this and answer a few questions. Are there any intermediates? Okay, what could be a possible intermediate? NO3, how do you know it's an intermediate? Right, it's a product and a reactant. All right, how would I go about figuring out what the net reaction is? All right, you add the top and bottom together and cancel out anything that appears on both sides. So if I add these together, I would have 2 NO2s. I'm going to skip the phases just because they're all gas. All right, how can I simplify that net equation? What would be one thing I could cancel out on both sides? Right, the NO3, because I just said it's an intermediate. Okay, what's another thing I can do to simplify this equation? Right, cancel out one over here and one over there. Can I cancel out anything else? No. Is it still balanced? Oh, question, Paul.
For the intermediate step, why is NO a intermediate step?
Why is this guy not considered
Yeah,
an
why is
intermediate?
it not an intermediate?
Because it doesn't appear again as a reactant.
Oh, okay.
Oh, yeah.
Why is NO2 not intermediate?
Oh, because it starts up as a reactant and makes a product. It's not the reverse. So let's go ahead and define it. For an intermediate to exist, or to be called an intermediate, you must make it as a product and then use it as a reactant. Which means it doesn't actually exist, right? Because as soon as you made it, you used it up. It's gone. Yeah.
So even if you cancel them in the net reaction, that doesn't always make them intermediate.
Right, which is why they're two separate questions. Okay. Let's say I tell you these pieces of information. We'll say reaction number 1 is slow, relatively slow compared to the other one. We only have two equations. One's slower than the other. Can't both be slow. if I know one's slow and one's fast, based on what we said in part 3 here, which rate is going to be a rate determining elementary step? The first one, right? So number 1, because it's the slow one, and the rate is determined by the slowest elementary step. Follow-up question to that. What would be the rate equation for rate law? Sorry, what would be the rate law for elementary step number 1? I'll help you out. That's helpful. What is the exponent that goes along with elementary step number 1? Okay. 2. It's the same two things. There's 2 of them. Right, I could have rewritten this as 2NO2.
What is the rate law on
Just number 1.
equation 1?
Yeah.
not the net equation?
Correct, not the net
Okay.
equation. How do you feel about that? Good? Okay. Okay, so building on what we just said, rule number 3. Oh yeah, question, Cody.
Where does the lesson on CO2 come from?
This and this.
No. Yeah, on your net reaction.
There and there.
No. Oh, I'm sorry, no, that's, never mind.
Oh, okay, okay. All right, so let's say we now know which ones are fast and which ones are slow. We know that the slow one is the rate determining step. If you have 3 reactions, you're going to have some combination of fast and slow. If it happens to be that's fast, slow, fast, well, then the fast step is considered to be at equilibrium. And why does that matter? Let's say, so this is my net reaction. All right, I got my net reaction. I have a fast reaction, slow reaction, fast reaction. Which one of these 3 steps will the rate law be based on? Step 2. So let's write out our rate law for that. Right, so the rate law for step 2 would be that. That clearly doesn't add up, does it? I am missing something. What am I missing? Oh, yeah, I'm missing a bunch of carbons. Okay, I'm going to rewrite them. You can either rewrite them or just try to squish them in. It's like you can't make H2CO if you don't have any carbons in there. There we go. That makes more sense. All right. All right, so now I have my corrected 3 elementary steps. The rate we just said is based on step number 2, where I have H and carbon monoxide, right? H ones, their exponents are 1. Does a single H appear in my net equation? a lone single H appear anywhere in my net equation? Single, solitary, lonely H in my net equation? No. That's an issue. You can't have a rate equation that is not based on your reactants, right? Because all of our rate laws are based on reactants. We now have a rate law that involves something that's not a reactant. Uh-oh. So this is not one of the reactants in net equation. Don't worry, I can turn that frowny face upside down in just about 30 seconds. I have a relationship between single H and H2, right? Two H's is H2. Is H2 something I can use in the rate law? Right, I can use it because it's in the original reactants. So what's the relationship between this H and that guy? It's an equilibrium. What's the ratio? Right, 2 of those to 1 of those. So I could either, probably the best way to do it, right, based on our step 1, 2 H's is equal to 1 H2. But in my equation, I only have a single H. So it'd be true to say that H is equal half of an H2. Yes?
How can we decide that the rate law is based on step 2 when both step 2 and step 3 are slow?
Because I miswrote. That should be fast. Yep. Sorry. I was trying to copy it down. That's wrong. There we go. All right, so now I have a relationship between single solitary H and H2, which means now I can plug this in for that.
Can you use that ratio using any of these steps?
In theory, you could, but you have to have one that relates the thing you're trying to get rid of with one of the reactants.
Okay, so it could have been step 3.
It can't be step 3 because HCO is not one of your
Or
reactants. If it was something else.
was step 3.
Yeah, yep, yep. All right. So now I have a rate law that relates my 2 reactants to each other. All right, so I've avoided the issue of having something that doesn't involve a reactant. All right, last thing to think about would be this catalyst and how it affects your mechanism. All right, let's say this reaction has that as its energy level diagram, or as its thermodynamic diagram. Is this reaction exothermic or endothermic? Okay. Does that mean it is likely to proceed based on your knowledge of thermodynamics?
Yeah.
It is likely to proceed. So we know it's a reaction that will go eventually at some rate. Let's say I do some work in the lab and I figure out the way it goes is something like this. All right. Looks just like the net reaction. I just split them up to make it more obvious. How many molecules do I have reacting together? I have 3, right? 3 things interacting. 1, 2, 3. Let me do a little sidebar. Make yourself a little. In this crazy last section of molecularity, if you have 2 molecules interacting together, it has its own special name. It's called bimolecular. All right, 2 molecules, prefix bi, 2, so 2 molecules. If you have a one single molecule reactant, kind of like we saw earlier where it was like ABC and it spontaneously explodes into individual parts, we're going to call that unimolecular. So when 3 combine together, sometimes it's called trimolecular and sometimes it's called termolecular, T-E-R, molecular. So looking at my mechanism up here, what would be most appropriate to call it? It'd be termolecular. Turns out in science, termolecular reactions are incredibly unlikely. The probability of having 3 things in space colliding together at the right time with the right amount of energy, very unlikely. So we don't run into these very often. Just as a fun fact, doesn't happen very often. All right, what if I wanted to write, I didn't mean rate equation, rate law. What if I wanted to write the rate law for this mechanism up here? What would be the exponent on my cerium? Okay. Yes, yep, yeah. All right, so I have 3 things reacting, right? Trimolecular, I just told you that's not super likely to happen. Okay, looking over here at our energy diagram again. If I add the catalyst, right, it lowers the activation energy. Does it make it endothermic? Does it make it more exothermic? No, right? Because exothermic is measured just reactants to products. Doesn't matter how big of a intermediate it has to get over. It's just this measurement, right? Because it was a state function. The state functions don't matter what the path is. It could be a large intermediate, it could be a small intermediate. Doesn't matter. It's definitely exothermic. So if I add this catalyst, my new elementary step is this. My new slow elementary step, because that was what I had up here. This was my. So if I wanted to write a rate equation, rate law, if I wanted to write a rate law for this now, what would be the exponent on the cerium? Okay, 1. How many reactants do I have colliding together? 2. What would I call that? bimolecular. And this makes it better because it's no longer termolecular. Bimolecular is a much more likely to happen. So the catalyst lowers the activation energy, which is a measure of likelihood of reacting, and so there's a better choice. Yeah.
Why did they include the catalyst in the rate equation?
Because it's an elementary step. The slow elementary step can include the catalyst, but not an intermediate.
Because we changed the last one, we changed it to 1/2 H2 because it wasn't on the product, they were originally reactants.
Right. The catalyst will they'll show up as a reactant. So it's a little different. All right. Last thing, and then we'll pass back the test. So this is the end of chapter, what chapter are we in? 14? 13? 14? 13? Whatever this chapter number is. In general, for all reactions, what you're going to do is, like you did in lab this week, right? You guys measured a bunch of initial rates. We can measure a reaction rate either through figuring out initial rates or doing my favorite thing, making some graphs. Once you figured out what the order of the reaction is based on these two things, you can put together the rate law. And then from the rate law, we can figure out what the correct mechanism is for any reaction. So, all right, I'll stop there. That way I have some time to pass back the tests. So when you come on Monday, bring equilibrium notes. And we're going to do equilibrium stuff and